Okay, good afternoon. I would like to start by thanking the organizers for giving me this opportunity to present our work here. So the title of my talk is Bound on Self-Interacting Dark Matter from Galactic course. Okay, so to start with, like many, I'm also a believer that dark matter to be of particle in nature. And so therefore, the best way to ascertain its particle properties and its phenomenological studies is to probe its interactions with each other. So in this case, one of the best things to do is one is to look into the interactions of dark matter with the standard model sector. And in this case, one can look into the effects of direct detections like in nuclear recoil experiments or sub-GeV dark matter scattering, or even in indirect searches like dark matter capture inside celestial objects, and also in collider physics where one can look into missing energies. Alternately, one can look into the scattering of dark matter within the dark sector itself, which is the self-interactions, and which is the title of this presentation. Okay, to start with, so what self-interaction does, it basically opens up a channel in which dark matter can now communicate with each other, and therefore, so there is an exchange of energy and momenta from the warmer peripheral regions to the cooler inner regions. So this kind of helps in thermalizing the central region of the galactic halos, and the extent of these thermalized regions is basically a function of the strength at which dark matter can interact with itself. And also, as very much evident from here, is that this kind of reduces the central density of dark matter at the central regions. Okay, so this is a very simplistic algorithm of the simulations that we have followed. So what we have done is we have simulated around many dark matter halos in the mass range of 10 to the power 10 to 10 to the power 15 solar mass. And we have considered a self-interaction cross-section of between 0 to 10 centimeters square per gram, where 0 is the collision-less dark matter scenario. And we have done this for around 10 to the power 6 number of dark matter-only particles. And for getting a better idea about the statistics, we have performed each simulation for a particular mass and cross-section around 4 times to get a more better understanding of the statistics. So once we have our simulations ready, the results are ready, what we do is we extract the core radius from our simulations. And as evident, this is a function of the halo mass and the strength of self-interaction. Also, alternately, we have looked into certain galaxies where we have looked into their observation data, and we have similarly extrapolated the core radius as a function of mass. So with these two parameters ready, we are now in a position to compare them and provide some bound on this specific self-interaction cross-section. Okay, so this is a result in product of our simulation. So on the left panel, we have plotted the velocity dispersion as a function of the radial extent from the center. So as you can see that a collisionless scenario is quite less thermalized, whereas once we introduce self-interaction, we see the core to get heated up and the effect of thermalization basically sets in. This same effect can be realized if we look into the density distribution of dark matter, where we see that as we keep on increasing the self-interaction cross-section, we see the number density to kind of go down, and the extent of the core radius also increases. So this is kind of what we expect from our understanding of self-interaction. Okay, so here just to give a brief idea about the statistical stability of the analysis. So on the left panel, we have plotted this delta RMS basically quantifies the goodness of fit of our simulations with the with our modeling. So as we see that as we move on to larger cross sections and larger mass halos, so we see that the fitting kind of falls a bit loose there. That is most likely due to the limit of our resolution. And on the right panel, I am showing we have performed a convergence test where we have looked into different number of particles, and we see that taking around 10 to the power 6, 7 number of particles is kind of okay because there is not much significant change in the density distribution, particularly at the central region. Okay, so this is the legacy data that we have used to compare our simulation. So we have used dwarf data from dwarf spheroidal, low surface brightness galaxies and galaxy clusters. So what we do is we start with the observed rotation curve and we convert them to density profiles using this simple-minded formula. So, and here I am showing the fits that we obtain for our simulation and the simulation for two different density profiles. One is the code NFW distribution, which is given in the red, and the green is the genes or the semi-analytic distribution. By the way, one can look into other distribution profiles as well, which we have, but we find that the errors in fitting is comparatively less for these two, so we have stuck with them. Okay, and here I have shown for different cross sections and the different masses for the density distribution and their corresponding fits, where the vertical lines is the estimated core radius for our simulated halos. Okay, so now since we have both the ingredients ready, so one from the observed data and the other from simulations, we are now in a position to compare them. So on the y-axis, I have the core radius as a function of the dark matter halo mass. And the left panel is for the semi-analytic distribution and the right is for the code NFW distribution. So here the three colored curves, orange, red, and brown are for three different values of scattering cross-section, whereas the magenta line is for the observed data. So, and the vertical lines are the error bars corresponding from simulation and the fittings related to, and the errors due to fitting. Okay, so finally, when we have both the core radius estimates ready, what we do is we perform a chi-square test, and where we try to constrain the dark matter self-interaction cross-section. So on the y-axis, I have the reduced chi-square, and on the x-axis, it is the specific self-interaction cross-section. The green and yellow panels are for the 1 sigma and 2 sigma confidence. And the vertical lines are the existing bounds from which are already available in literature. So as one can see that for the wide range of halo mass that we have considered here, the semi-analytic distribution prefers a zero scattering cross-section, which is the CDM scenario, whereas the code NFW profile prefers a small but non-zero scattering cross-section. Okay, so finally to summarize, so dark matter self-interaction leads to thermalization and helps in core formation, and the strength of which is kind of governs the extent of these thermalized regions. And comparing the distribution of core radius as a function of the dark matter halo mass from simulation and astrophysical observations can provide a useful handle to explore dark matter self-interactions. So for our case, a very simplistic velocity-independent point-like isotropic interaction, we provide a conservative bound of around 9.8 centimeters square per gram at 2 sigma confidence. However, the bounds that we present are very much sensitive to the distribution of dark matter that one takes into account, particularly at the central region, and obviously they are very much sensitive to the resolution of the simulation. Thank you, and this is based on this work, which has been done in collaboration with Tirtha Shankar Ray and Abhinash Kumar Shaw. Some questions?
Questions?
Nice talk, thanks. So you simulated these halos? How did you initialize them? Are they isolated halos? And if so, yes, how are they initialized? They're isolated halos. So how do you initialize them? What are the initial conditions?
So what we start with, we have started with a cusp-like initial condition, and we have seen them to thermalize once we evolve them with self-interaction.
And if you initialize a simulation like that without self-interactions as just a cold end body simulation, does it go to like some expected NFW like profile?
Yes, yes.
It's consistent in the zero cross-section limit.
Yes.
Thanks.
My question is regarding that velocity dispersion as a function of radius and the density. So does that profile depends on whether the self-interaction is kind of attractive or repulsive?
No, so this is just like a point-like interaction. Okay, so if you look into, I mean, it's like a hard sphere scattering. So are you talking about the velocity dependence?
I'm asking, does this depend on the kind of interaction that the dark matter particles are having, like attractive or repulsive? I mean, effectively.
Oh, okay, yes.
Yeah,
okay.
yeah.
You can approximate like that, but however, I mean, the nature will be same if you consider any other kind of profile. It won't be very different because this is like just a change. I mean, this plot just tells you that when you introduce interactions, what happens. So whatever model you take, this simple feature will exist.
Because the way I will think is like if.
How do you define the core radius for these analysis?
Okay, so like I've showed some profiles over here. Okay, so if you look into the semantic profile, so you see that within this radius R1, it follows like an isothermal distribution. However, outside it again goes down your regular NFW. So this R1 is kind of acts as an estimate of core radius for this profile. However, if you look into other profiles like we have done here, so this has an innate core parameter. You can also find other distributions which similarly have an innate radius distribution.
One last question.
Hello. Yeah, so I was wondering, does this core cusp problem that SIDM tends to solve, does it depend? It depends on the cross section, no?
Yes, cross section is an important parameter.
Yeah, so if you have like very large cross section, around 10 or something, so how would that affect the problem, like the core cusp problem? And
so the issue is to solve the core cusp problem, but again, you have like different class of galaxies. You look at like you have different relative velocities. Like for Milky Way, you can have around 200, or dwarfs around 10 to 20, or clusters maybe around 1,000. So in that case, you won't have like a single scatter might not be good for everything, single strength.
But sigma V has to be same, no?
Sigma V?
Sorry? Yeah, I mean, the cross section.
Sigma over M, right?
Yeah, sigma over M. And that has to be one fixed value, or it can be variable?
Yeah, it can be variable. Like here we have tried to do it like we have considered one value that tries to solve for everything, but that is very, again, a conservative bound, because a more idealistic way would be to have different at different velocities.
Right. Okay, thank you.
Okay, let's thank our speaker again.